So I'm Bill Bain. I'm going to talk about stream processing. So follow up on the previous talk, which was, how many of you were here for the Redis talk? Just want to know what context we have. Good, okay, because I'm going to make reference to some of the things he talked about to show some of the similarities and differences in the approaches. So we're going to talk about data parallel analytics and how that could be integrated into stream processing using in-memory computing techniques, in particular in-memory data grids. So I'm Bill Bain. I'm from Scale Software. We have a booth if you want to stop by. We do in-memory computing. My career has been focused on data parallel computing since, I hate to tell you when, 1978. And we do two things with our in-memory computing platform. One is we scale application performance using in-memory data storage techniques not unlike the ones you just saw. And also, with in-memory computing, we allow our customers to track live, fast-changing data to give them what we call operational intelligence, the ability to react in real time and provide feedback to a live system. So this is the agenda for today. We're going to talk about what we think is the next generation in stream processing. It's interesting if you were at the Redis talk, you know, the focus traditionally has been on moving data through a stream processing system and looking for patterns and trends, tracking each of the events. But one of the real challenges is to migrate to stateful stream processing, where you decorate those events with state about the data sources so that you can learn more from the events and give better feedback and better quality alerts because you can introspect more deeply on the data. So we'll look at how in-memory data grids as a technology help us to do that and how we can use this so-called digital twin model to accomplish it. And then how do we integrate data parallel computing into this so that we can find aggregate patterns and trends across all of the data sources. So stream processing has been around for a while. Many applications for it, as you see here. And really the challenge is to take thousands of data sources, correlate those events to find patterns and trends, and to provide the feedback and alerts, and also to find the aggregate patterns across all the data sources. So that's the big picture problem we're trying to solve. And here's an example, one that we've looked at quite deeply. My colleague here, Oleg, who's going to give a demo hopefully at the end, if I don't run out of time. It's this area called e-commerce recommendations. And if you think about it, e-commerce recommendations is a stream processing problem. You have thousands or hundreds of thousands of e-commerce shoppers making clicks, and clicks become events flowing into a recommendation system. And the goal here is to learn about the shoppers, what are their preferences, what are their demographics, what is their previous shopping history, integrate that with the clicks that are flowing in, telling the system what products they're browsing, find the patterns across those products to try to deduce what they want, and then to make in-the-moment, real-time recommendations in under 100 milliseconds so that they can decide what's the next product to view and whether to put products in the cart. And along with that, there's the challenge of how do you look at what all the shoppers are doing, find aggregate patterns such as the most viewed products, the most popular products that have sold today in various categories, various brands, and then optimally feed that back to the shopper so the shopper can benefit from seeing what other shoppers are doing, and the merchandisers can decide what special promotions they might want to do. So it's a very interesting stream processing problem, and this is an example of what it might look like from the shopper's point of view. So as the shopper is perhaps setting preferences about the products, we're looking at refrigerators here, and also looking at, oops, that's why everybody does that, because I was watching this in the previous talks and wondering why the laser pointer, because the laser pointer and the forward are right next to each other. Okay, there we go. So this is, we can look at the various properties of these products, like which brand we want to look at, LG refrigerators, but then we also can look at what's the collaborative feedback from other shoppers. And you can see from this, you know, what's the best-selling product today? Is it an LG refrigerator or something else? And therefore, make decisions based on collaborative opinions of all the other shoppers. So that's a case of where parallel computing needs to be integrated into stream processing to provide real value to shoppers. And there are many other cases of that. This is an example of the output of data parallel computing from this e-commerce recommendation platform. Here we're looking at statistics about the shoppers, the most popular brands and products within brands. This shows you the most popular products, and you can also select most popular brands. And other metrics which have been collected over the course of just a few seconds across all of the 100,000 shoppers on an e-commerce shopping site. And the trick is to make this available in real time and not after the fact in a data warehouse or in a data lake. So this is the challenge that stream processing architectures face, and this is how they're typically handled. If you look at some of the traditional platforms like Apache, Flink, Beam, before that Storm, stream processing systems are typically organized as graphs or linear pipelines with pipeline stages from the sources to the sinks. And what's happening is you have your thousands of data sources generating events. And the challenge is, how do you write an application that runs in a set of pipeline stages that's extracting value from all of these events? In particular, how do you correlate these events by data source so you can see what a particular, say, e-commerce shopper or IoT device is trying to tell you? And how do you embed your application-specific code into this system so that you can do something it's not too tied to the overall architecture, like the Flink architecture, for example? And also, how do you add state to this? Because the challenge is that you want to have context. Like if it's an e-commerce shopper, it's their preferences, their demographics. If it's an IoT device, it might be its maintenance history, its model number, its temperature over the last couple of hours. If it's a patient in a medical system, we'll see all of these examples in a minute, you want to know their medical history. You want to know what medications they're taking. You want to know any events they might have had, so that when you get telemetry, say in an ICU, you can analyze that telemetry with a deep context and thereby do a better job of stream processing than if you're just looking at, say, a Twitter stream and trying to find sentiment or something across the whole population. So it's really taking stream processing to the next level. And the challenge with traditional stream processing architectures is that there's no way to describe state. This is done on an ad hoc basis, and usually with a data cache or a database that's held aside from the stream processing pipeline, and it's really up to the application to take advantage of it to store state there. And that creates two problems. One is an architectural problem. It's hard to write applications where the state is being managed in an ad hoc manner. And second, it creates a network bottleneck. And I think if I click, I might see a circle, yes. So that's a network bottleneck, because every time you go to retrieve state when processing an event, then you have to generally go across a network to a distributed cache or to a database, even worse, to retrieve the context that that event should be analyzed in. And so that creates, that slows down the latency by which you can respond to events and provide feedback. Also, there's simply no discussion about how do we do data parallel analytics. It's just, there's no architecture for it. It's a stream processing pipeline. Okay, so people have generally punted on this, and the Lambda architecture is the popular architecture for describing how batch analytics and stream processing are to be integrated. This is the way that people have thought about this over the last several years, and the answer is let's just separate the analytics out into a different path, a slow path, and keep the stream processing in the fast path. So we're not even going to try to solve this problem in the fast path. We'll just dump the data into a data lake and do this with Spark or some other technique offline. And that's great. It allows for deep introspection, but it doesn't give you real-time feedback or so-called operational intelligence. And so the real challenge is, how do you combine stream processing with state, so you have stateful stream processing, in a coherent architecture that gives you high performance and ideally integrated data parallel analytics? So let's go take a look at this technology area of in-memory data grids and see how this technology helps solve this problem. We discovered this a few years ago when doing data parallel analytics with our grid, and then our customers were pulling us into stream processing applications. I talked about a few use cases yesterday. One, for example, a cable company with cable televisions all over a community looking at channel change events. And that turned into a stream processing problem. The e-commerce recommendation problem is also, as I said, a stream processing problem. So in-memory data grids are not unlike Redis data stores, if you saw that. So actually, it's very interesting to say, what are the key differences between traditional in-memory data grids, the way you would find with some of the other vendors, and what Redis is doing? And unfortunately, that's a different talk. But I might just touch on that for a minute in the next slide. The idea here is that in-memory data grids are key value stores that are storing objects in a logical collection. In our particular case, we actually have overt collections. Redis, as you heard the talk before, they don't actually keep namespaces, but most of the vendors do have namespaces of objects because in an object-oriented view of the data, they're typically objects of a given type from a given class definition. So you might have cars in one and wind turbines in another. Okay, so they're objects which are accessed as a key value store, NoSQL key value store, but it's really business logic state. They're typically hydrated into Java objects or C# or C++ objects and interpreted as such. That's why we don't use a SQL view of data, relational view of data in the in-memory data grid. Now, the job of the in-memory data grid is to distribute these logically described objects across a cluster of servers to achieve two goals. One is transparent scaling, transparent load balancing for scaling and scalable throughput, and second is for high availability. And one of the ways in which traditional in-memory data grids differ from Redis, a topic that didn't come up, is Redis uses what's called the eventual consistency model, which means when you do a write to an object, it will update one of the grid objects and then send an update to another one for high availability, but it doesn't wait for that reply. And that gives you speed, and that's why you saw those really high throughput graphs comparing Redis to the other products. But if you have a failure, then you can have stale data in the grid because one of the replicas may not be coherent with another replica, and so you may have data incoherency. So in our particular product, we use what's called a sequential consistency model. But those are just, it's in the CAP theorem, those are just two different points in the space that you might want to occupy. But I thought I'd make that point in passing. Different applications require different levels of consistency. So what we're doing is leveraging commodity servers or cloud instances to scale the throughput, achieve very high throughput and low latency. When you have scalable throughput, you have fixed latency for data access or for data computations. And that's the purpose of linearly scaling the throughput, is so that the latency doesn't grow. And at the same time, you're avoiding data bottlenecks because you can, with an in-memory data grid, you can do computation directly in the grid. It was what we'll see for the rest of this talk. And so instead of just using it as a passive cache or a store, you can migrate computation into the grid and perform it there in the grid. And that's another interesting parallel to Redis. I often do this. I hear a talk, I want to talk about it in the next talk, so I hope you'll forgive me. So Redis, we saw all those data structures, right, in Redis? And that's really an example of interpreting the objects in the grid with code that's running in the servers. And so there's sorted sets, for example, hash tables. They've added code inside of their grid to interpret those objects and thereby streamline the path from the client to the server. So there's another way you can think about doing computation in the grid. This is a path we chose for a different set of trade-offs, and I'll explain that. The way we do computation in the grid, and another way to think about it, is to have a separate process on each grid server in the cluster, which is hosting a language runtime, a Java runtime or a .NET runtime, so that user-defined code can be shipped out to the grid and run in the grid. And this allows us to do data parallel computing and also to do stream processing. And we'll talk more about that in the following slides. What's interesting about this design decision is that it's separating the user code, so what Redis calls modules, we could call invocations that are running in an invocation grid. They're running in a separate process to isolate them from the grid service so that if there's an error or a failure in one of those user-defined applications, it doesn't affect this, the stability of the overall grid service. And there's another reason to do that. One is that we can follow this nice object-oriented model, interpret the data as objects in Java or .NET, and also we can access objects uniformly across all of the grid servers. So if you're going to do if you're going to implement MapReduce, which we'll see in just a minute, you need to be able to see objects in other grid servers. So the approach of doing Lua scripting inside of the grid service only gives you visibility to the local objects. If you take this approach where this is more of a client, then you're paying a performance price because you're not running in the grid service. The data has to move across an IPC connection between two processes in a server. So that's a performance penalty. The benefit you get is a distributed view of the data and isolation. So I think that's enough said on that topic. It's an interesting comparison, I think. There's no right or wrong way to do these things. They're just different trade-offs. So there's two types of parallel computing that can be accomplished with this invocation grid approach. One is doing stream processing, where every streaming event is sent to an object in the grid for processing, and we'll see the leverage that gives us for correlation in just a few minutes. If anybody has their business card, gives it to me, I'll send them the slide deck, so if you don't need to take pictures unless you want to. The other approach that it can be used for is to write data parallel computations, where you define a class method on a type of object running in a namespace in the grid, and that's executed in parallel across all the grid workers, and the results are merged and returned back. This allows you to do aggregate analysis. And what's interesting is you can do aggregate analysis at the same time you're doing stream processing on the same collection of objects, and we'll see that in just a second. So an example of that is this is a data parallel execution paradigm or technique, and we selected it because it was very popular for parallel supercomputing going back to the big supercomputers designed by the national labs and the company I worked for, Intel, back in the early 2000s. And so it's called parallel method invocation, and what you do is you describe one class method on a type of object that operates on all of the objects in the grid, and it's going to evaluate and analyze those objects and produce results. And these results are then merged with another user-defined method called merge here. And then you finally do a distributed merge. The platform runs a distributed merge and returns a single result. So if you studied Hadoop and MapReduce, you go, wow, that's different, isn't it? Because you get a distributed binary merge, which is done, by the way, so that it'll run in logarithmic time. But it's a very simple way to think about data parallel computing. It turns out it allows you to build MapReduce very easily, because MapReduce is really two phases of that. So what is MapReduce? MapReduce is really do data parallel computing with group by first. The map phase is group by. So you take the source data set and you combine and map all of these objects using this user-defined map method into a set of partitions. I think there's a picture of that. Yeah. And these partitions then, on those partitions, you run a second data parallel algorithm using the reduce method. Reducing is not so much reducing as it is analyzing the partitions and producing results. So this is one PMI, and the map phase is an earlier PMI. So therefore, you can implement MapReduce, and we've done that in our platform. Implement MapReduce as two phases of PMI. Well, here's something interesting that you probably haven't thought of coming from the IMC community, is that there's yet another way to do this that we stumbled across because we have people that work with .NET a lot. And .NET has a thing called parallel ForEach. How many of you have seen parallel ForEach, know about it? Okay. All right. So there is some knowledge of, probably you know more about it than I do then, because I'm not one of our .NET developers. But it's just a variation on PMI in some sense when it's made distributed. Distributed ForEach is a term we coined to extend parallel ForEach across a cluster. All it's doing is taking the eval, what's called the body here is user-defined code, is doing an eval with an iterative merge. So you start with some initialized result, and as you do evals, you do merges on the fly, and you do that for each core, right? So there's a task per core, theoretically, or something approximating that. And then finally you do a merge within the server and then do merges across the servers. So it's really a variation, but what do you think is the benefit of doing that? Can anybody say what they think the benefit is? There's a huge benefit that's not at all obvious. And I don't think when the people created it in, well, maybe they did, I guess.
Better pipeline because you don't have to wait for the storage the way that MapReduce does.
Well, it's reduced garbage collection, because you eliminate all the intermediate objects that are created by the PMI that I described. So if you look at PMI's garbage collection, it's humongous, and the performance just gets a lot better because of the fact. So yes, it's improved pipelining in the sense that you're not garbage collecting on the fly. So yes. But anyway, that's just an interesting aside. The point of all this is, yes, there are techniques for doing data parallel computing with in-memory data grids using an object-oriented view of data. And now let's apply that to stream processing, okay? So we'll come back and do that. First, we need a domain for data parallel computing, and it's the digital twin model. This is what we have observed is a very effective model for hosting data about stream sources, collecting that along with events, and then doing stream processing with deeper introspection, and then leading to data parallel analytics. So this model, this so-called digital twin model, is a heavily overloaded term, and it's not really a term that's used in streaming analytics. It's a term that comes from product lifecycle management. It was coined or created by Michael Greaves at the University of Michigan, I think in 2002 or thereabouts, and it's been popularized in 2017 by Gartner and for use in streaming analytics, as well as product lifecycle management. And so the idea behind it is for every data source, you can keep an object in the grid, which is hosting the context you need to do the introspection we talked about. In particular, state information about that data source. So if it's a car, you know, you can imagine all the things. Its speed, its position, the driver's driving history, whether the driver has a record of speeding tickets, you know, all kinds of information. Context that allows you to interpret the telemetry with deep introspection. In addition, that event collection that we saw the Redis is implementing, you can be hosted inside that object too. So in some sense, well, let me get to that in a second. Along with that is the analysis code to both maintain this event list and then to analyze the combination of the event list and all of the context so that the alerts can use all of that information. So it's if you will, if you want to think in Redis terms, it's a user-defined module that's created on a per digital twin basis. So it's a dynamic module, dynamically generated code by the user to interpret incoming events with rich context. And I think I'll stop talking about Redis from here forward. But you get the idea that you're doing this interpretation in the grid, computing in the grid, as opposed to pulling these objects out to a client and very efficiently processing them there. So what are the benefits of this? First of all, it's a very structured approach to stateful stream processing. The context is structured. You can see what it will be. It's also, it's at hand. You don't have to go across the network to get at it. The events are shipped to the grid. The code has already been shipped to the grid. So all of the work is being done in situ, in place, within a grid server. It allows you to implement user-defined algorithms. This is a really interesting thing. You can extend this. You can put an ML algorithm or rules engine in one of these parallelograms and embed that. And the grid is really just orchestrating the execution of the user-defined code. Most of the time, this code is highly proprietary, whether it's a financial services company or a cable company that actually, they wouldn't tell us how they filter channel change events to know whether somebody has been drinking too much and they actually have thought all about how channel change events, what their time delays mean. And that's absolutely a secret. So most of this code is secret, and it's nice if the platform can orchestrate it without the code having to be embedded into the artifacts of the platform, the APIs. The way when you would write, say, a Flink algorithm or a Spark algorithm, you're really writing to the platform as opposed to writing code that's run by the platform. A subtle distinction, I think. But lastly, and the topic for today is it's a really good basis for aggregate analysis because now you can do data parallel analysis across the twins. What time is this supposed to be over? 3:30, okay, thank you. So here are some examples. I think this is self-explanatory. I'm not going to read this whole table, but it's interesting. There are countless examples. We think IoT is going to be a big area for the digital twin because devices and digital twins are very natural companions, if you will, or twins. What you do is you can receive device telemetry and then write predictive analytics codes so that you can determine whether or not to alert to shut down a system. One of the things we learned in doing this is that the engines that run inside of these large ships are so expensive that to predict a failure and shut them down before it occurs is extremely important to the cargo industry, the shipping industry. So medical monitoring, I talked about that. We actually had a discussion with people at SUNY in New York who were saying that we have the knowledge that physicians have the knowledge that if they can look back over several hours when you're in the ICU or getting telemetry, they can make much better predictions than if they just walk in and look at what the graphs and charts are saying at that moment. But they don't have the bandwidth to do that for everybody. However, a digital twin system can embed, with a rules engine, for example, the knowledge required to interpret the statistics, the telemetry, and create alerts much more intelligently if the context is present. We talked about cable TV, e-commerce, fraud detection, or security perimeter analysis. These are other applications, not to mention financial services and tracking the market to make trades. For example, an example I gave yesterday is a hedge fund tracking market price changes and looking at portfolios and then triggering trades to rebalance on the fly. So the question is, how does this marriage work? Why are digital twins and in-memory data grids good? Why is an in-memory data grid a good host for digital twin? And I think we could see that now, right? Digital twins are an object-oriented context for doing stream processing, and in-memory data grids are really good at scalable object-oriented storage. And you get a lot of benefits to that. You get scalable throughput. You get a domain for both scaling stream processing and scaling data parallel analytics with an in-memory data grid. So you also get automatic event correlation. It's somewhere up here. I don't know where it is, but yeah, right there. So as events come in, they are directed to the digital twin object representing that data source, so you get very nice correlation. If you think about it, data correlation is the #1 problem that you face when writing a stream processing algorithm. Going back to the cable company that I talked about, in order for them to look at cable channel change events and give recommendations to their cable viewers, they have to correlate all of these events and come blasting in over their multiplexers and see which came from which cable box. And that process was taking this company 6 hours. And by using a distributed cache, they thought they could get it down to 12 minutes. But by using this digital twin approach, it can be done in a few seconds. So that's the difference. Leveraging the correlation and doing the computation in the grid allows this to be a very effective platform for stream processing. And also it can be aligned with Kafka ingestion. This is just an example of how data ingestion can be scaled along with the grid. So you probably know that most in-memory data grids are partitioned or sharded across multiple servers. That's a typical technique. Well, it turns out that Kafka brokers are sharded as well. And Kafka is extensible in such that you can align the sharding so that when an event comes in, that event for a particular device can be directed to one of the partitions on this server and not be sent to a server and then having to be forwarded to another server. So it's very, very nice to align the ingestion platform with the execution platform of the IMDG for stream processing, and that can be done with Kafka. So now let's talk about data parallel processing. So we've seen the digital twin model is very effective for handling incoming events, providing the correlation. It also allows access, as you might imagine, to offline state. There we go. There's our offline state within the stream processing. In addition, this analysis code that's analyzing the events as they come in can be supplemented with analysis code which is extracting data out of the context there and then doing a data parallel analysis like a MapReduce and returning those results, either feeding them back into the system and storing them back in the state or sending them to an analyst. And we'll see some examples of that. Here's one example, the e-commerce shoppers. So as the clicks come in, the data that represents the shopper can be hosted in a digital twin object in the grid, and that would host the demographics, the shopping patterns, as well as the click stream and the products that have been viewed by that shopper. At the same time, the data parallel analytics can be looking at all the shoppers and reporting to the merchandiser and feeding back. Here's another example for a fleet of cars. And I think you can imagine all of the things you could do here in terms of watching all of these cars, looking at their telemetry, say it's a rental car fleet, looking for speeders, looking for lost vehicles, providing alerts back to the cars. You know, you've left the state, you're not supposed to leave the state. And that requires having context for the car, the contract in this case, and knowledge about the driver. In addition, you can find aggregate trends and optimize overall operations. Okay, so here's an interesting artifact of the digital twin model that you might not have thought of. A digital twin can be organized into a hierarchy. So they don't just represent devices or physical data sources, but they can represent subsystems within a complex system. And by doing so, events can be sent upstream from the lower level digital twins to higher level digital twins. And these digital twins can operate at higher levels of abstraction, much the way our nervous system and our brain works, right? So in this case, this twin here is actually worried about the overall condition of the tower system, all the components, not just the blades or the generator in this wind turbine. And this twin here is concerned with the blade system and the control system and making sure that any kind of events or outages or problems are understood at a higher level of abstraction than the details of, say, the blades themselves. And you can think of systems like spacecraft that have complex hierarchies of control systems using this model, because this model lets you have a very natural way to componentize, to modularize the logic within the stream processing architecture with context, and also to communicate both up and back down to command the physical devices. And interestingly, this can be used with full object-oriented techniques. This slide just shows you how you could use inheritance to build digital twins. So this would be a design for a basic controller, and then you can build, say, a hot water valve controller, which has all of the artifacts of the basic controller, but then adds more methods and properties, right? Now, the hierarchy we just looked at is really just a set of these twins of instances, not to be confused with an inheritance hierarchy. This is a hierarchy of instances that are actually communicating up and down the hierarchy. So commands can be sent down, and events can be sent, and alerts can be sent up, and with a uniform messaging scheme. Notice that all three of these, the hot water valve, the circuit breaker, and the pump room controller in this very simple example, all are inheriting from basic controller, just to show you how inheritance and hierarchy are both used with the digital twin model. I think one of the most exciting things is edge computing, and that's where the digital twin model has yet more benefits, because it can ship, because digital twins can be shipped out to the edge without having to rewrite the code. So a digital twin controlling a blade could be if you have the intelligence, you have the processing power, you can just move the digital twin from the cloud out to the edge, change the WAN protocol, and now you have rehosted this twin without having to rewrite it and rethink it. So we're modularizing the stream processing and then distributing it in the network where it best fits. And by the way, this is a very simple example. What you typically would do is break this twin into two twins, a low-level twin and a high-level twin that remains up here doing higher-level analytics. But you have a nice modular basis for implementing both the code and the data for the stream processing model. And so the digital twin model seems to have, every time we look at some new attribute, there seems to be value here. There was a talk earlier today, the gentleman from Salesforce talking about networks of users and how are they connected. And I was trying to think how you could use this digital twin model to represent users in that network, and they can ship messages back and forth and track the connectedness using a model similar to this. So I think there are a lot of uses for it. So just now let's focus in as I wrap up here, and then we do a demo of this. We're going to do a demo of this. Of heart rate watch monitoring. So think about Orange Theory or something like that, where everybody's doing an exercise and getting telemetry on their watches that's being sent into the cloud for analysis. So the digital twins run in the cloud, and as we said, we're doing stream processing and data parallel analysis, the results of which can be fed to an analyst or fed back to the user. So this is code now. I'll do it quickly, because nobody wants to read code, right? But I just want to give you an idea of what it really looks like, so it's not just broad brush hand waving like this. Okay, so this would be an example of a digital twin state object, right? And you can see what's interesting here is you can have this is about a user of a heart rate watch, right? So you could have a list of their heart, any incidents they've had with their heart, the list of their current medications, in addition to their height, weight, and the exercise they're doing, and so forth. So then you can have a list of the telemetry. So this is the event list that we talked about before. So that's what a state object could look like for a digital twin. Now let's look at the code. So the code this is two more data structures. One is the heart rate event itself, which is pretty self-explanatory, and let me go back. And then also the alert going back to the user. So the heart rate watch is giving telemetry about who the user is and what has been observed, the current heart rate at a given time and so forth, and any other exceptions. Now, so this is this is the plumbing code, unfortunately, but this is how, and again, I'll send you the slide deck if you want it. So this is all in. This is just one way it could be implemented. One of the things we learned that the ReactiveX extensions are a very low latency technique for distributing events to an in-memory data grid. So this is an implementation of ReactiveX observers for this application. So this code at the top is defining the observer, which is going to process a running event. And this thing is then hosted in an invocation grid using this code here to spin up a new invocation grid and to start up this action, which is a heart rate observer, which will run that method. Okay? So it's just plumbing to start up the whole execution environment. And by the way, this is where the code is shipped out. The application code is shipped out to the grid servers and hosted in a JVM at that point. So I think I had a little help there, but there we go. So then when an event comes in, it's posted to the grid using ReactiveX, as shown here. What's key here is that the user ID from the heart rate watch is used to create a key, which finds the object, the digital twin object in the grid, to which to direct this event. And when the event comes into the observer, then the first thing that happens is the observer retrieves, this is that process event method I showed you a second ago. It retrieves from the grid the digital twin object, and then it runs the analytics code defined. This is this application-specific code that runs for this object and gives it the heart rate event. And then if the object has changed, it updates it, and it typically would change. So I think I'll use the blue arrows this time. This is the analytics code. It's just to give you a sense of what does message processing look like. And it turns out it looks a lot like Flink, except it's in the context of all this user data. In particular, the first thing that's done is time window collections are being created here. Out of that event list that we saw a minute ago, you can create windows as an iterable that you can iterate through to analyze heart rates over time from past events and current events. This current event is added to the list, and then this code is used to analyze the time windows. And then lastly, further analysis is done about the context. So we're looking at the heart rate changes in the context of this user's medications and medical history and recent events, injuries they might have, how long they've been exercising, what exercise they did previously, all kinds of things. This is sort of a roll-up of all the kinds of things you can do when you have the context in hand. You can look at such things at, what sessions they've been doing, what's their session history and what types of exercise, of course, all their medical conditions and exercise specifics, injuries and so forth, as I mentioned. So now you can analyze this event in a very rich context and get much better alerts and feedback. In particular, you can notify the participant to either, do another exercise or terminate the session, or if you look at the aggregate statistics that are being computed and feed them back in, you can alert the participant if their behavior, their heart rate, their metrics deviate dramatically from other users of the same type. So let's next look at how we compute those aggregate statistics. So we're doing both stream processing and looking at data parallel statistics. So this is how one does a data parallel computation. This is with PMI, the parallel method invocation. In Java, you simply implement an interface called invocable right here, which has two methods that have to be overridden, an eval method and a merge method. And so this is where the interface is between the orchestration and the user-defined code, which is just encapsulated in this method called merge, which is probably badly named for this example, since I've been saying merge in another context. But this is the user-defined code. This is just a very simple version to give you an example of it. And what it's doing is it's looking into that state object and it's collecting statistics. in particular, it is doing a group by here. This is an ad hoc group by without a formal MapReduce. So it's just collecting average heart rate and average BMI across all the users to give you a sense of what you could do with a data parallel computation. The interesting thing is to see how easily it is glued in by implementing this interface and then just plugging in the user-defined code on the user object on the digital twin. You know, the rest is just up to the user-defined application. And so this is how this would be invoked. And typically, this would be invoked by some service that is running once a second, once a minute, to collect aggregate statistics. And all it has to do is to run one line of code here, one statement, which is to do an invocation on the grid, on the namespace that is holding these digital twins and calling that class, that invocable class we just saw, and that causes that whole PMI and the merge to occur, and the result, the data parallel result pops out, you know, several milliseconds later, and then that can be stored or printed. So data parallel computing on an in-memory data grid in an object-oriented way is very straightforward. It's, there's not much to it, and yet it's extremely powerful because what are we doing here? We're not having to put data in the data lake and doing this later with Spark with a completely, in a different environment. You know, we're not running jobs. We're not doing batch processing. We're running program statements which are really, there's finer grained than batch jobs, and so the latency is much lower. And therefore, you can get results within, you know, tens to hundreds of milliseconds and be able to react to that. In particular, this can be fed right back into the stream processing as I described. So I think I explained how this would work, and I want to give him time. I'm going to wrap up with this slide and then a wrap-up slide and then go to the demo. OK. So what we're doing here with the digital twin model is, and I think this, if you just look at this picture, the interesting thing that it's doing is it's taking all of these events and it's correlating them by data source and encapsulating all of the relevant code for analyzing this type of digital twin, and doing that by using in-memory data grid objects. And these objects form a domain for data parallel computing that the results of which can be fed back in to this stream processing. So it's a very nice lever for doing stream processing and data parallel analytics in a unified software architecture that has rich context and is stateful stream processing, and eliminates this bottleneck that we just saw a few minutes ago. And, you know, and as I mentioned, the effect of that bottleneck is it reduces throughput scaling. And when you reduce throughput scaling, the latency goes way up. So you want to make sure you eliminate that bottleneck. So I think we see how, for stateful stream processing, a good path to look at is this digital twin approach, because of its ability to add state in a very simple, object-oriented way that separates application code and state from the orchestration done by the platform, and allows us to do real-time data parallel computing. So Oleg, go ahead, and we'll just show you that application running to give you a sense of what it's like. While he's setting that up, are there any questions? OK.
I want to show the heart rate sample application in action. This is the Java app, and we have two processes basically here. One is one application generates the user activity. So we model 10,000 users, 10,000 runners in this case, of different ages, different conditions, medical conditions, and another application simply displays that data for easy consumption. So I'm going to run the user simulator here quickly. So we start producing the data, and second process will just start a pretty simple dashboard which will display the results. So while it's collecting the data, here behind the screen we see the Scalable management console, which should now see we should see the activity on the grid. This is of course the grid running on one single machine, which is my laptop. But for interest, the sake of interest, I actually replicate that data back to Seattle here. So we do support replication from store to store. So that will be a good example. So let me see. yeah, so the application starts working, so we'll see data pretty soon. So what it does, it as I said, it models users of different ages, and then we can see then if, for example, a certain runner exceeds the threshold for because of the age or because it has a certain medication restrictions, the application generates alert that's sent back to the user, for example, or it could send, if it's a hospital environment, it will send to the doctor. So that kind of illustrates that the parallel processing we have, it's beneficial for the device itself, or the user, in this case, the entity we model within the digital twin, as a digital twin, as well as the some other recipients. So you can see here those alerts. We actually tell whether it is. Let me just see one of them. This is the alert. We exceeds the rate exceeds medication defined threshold, and some other alerts. I think we'll see the exceeding the. There's also medication exceeding the age restriction for the certain runner, and then, as I said, besides that, we do the aggregate computation. So that's in addition to the stream processing, we do the aggregation, which is allowed by nature of our grid. So we do that in parallel. So if I would have like 10 different laptops, you will see that aggregation still will be displayed as is. We'll do the merge across machines, but this is a one machine application. You see the average heart rate per BMI and average heart rate for the age bracket. So we calculate that in real time based on the data we receive from the application. So that's just this very simplistic example of how you can encode and solve your business problem using the API and the compute capability of the data grid. On the top of that, I think we're making the next step to simplifying the API, and we're going to have a library which will be a digital twin centric. So it will simplify the usage of that model within the data grid and the stream processing in general.
So you see the aggregate statistics being regenerated as well.
If you have multiple machines and you have Kafka brokers running side by side with us, you don't want to send that message from a Kafka A machine to scale out B machine. You want to say the event on machine A actually gets delivered to the same server. Either on it will be consistent. So you try to avoid the data motion and the unnecessary network hop. Right. Yes. On the same server. Yes. So in this case, yes. So you want to go specific on consistent servers. So you kind of map all the partitions and you have a predictable performance.
Okay, I think it's, we got one more minute. Any other questions? Well, thank you very much.